Welcome back to Industrial Automation course, Lecture 9, Programming Counters. Today's topics are as follows. Describe the functions of PLC counter instruction. Describe the operating principles of a transitional or one-shot contact. Investigate different PLC counter types. Analyze typical PLC counter ladder logic programs. Apply the PLC counter functions to control systems. Apply combination of counters and timers to control systems. In follow, you could find YouTube videos on using counters in codices. So if you are seeking further instructions on how to use codices, specifically counters in codices, please refer to these following videos. Counter instructions. Program counters serve the same function as mechanical counters. Every time the actuating lever is moved over, the counter adds one number. So here you see one mechanical counter, and we have a lever. Every time we move the lever, then basically we count one number up. Resetting to 0 is done with a push button located on the side of the unit. So we need to reset the counter in one specific point, and counters in PLC almost work the same as mechanical counters. Electronic counters can count up, count down, or be combined to count up and down. Although the majority of counters used in industry are up counters, numerous applications require the implementation of down counters or of combination up-down counters. All PLC manufacturers offer some form of counter instruction. One common counter application is keeping track of the number of items moving past a given point. So here we have a PLC and a sensor, and parts are moving on this conveyor. Okay, so we want to count the number of items passing from this specific point. So we need to have a counter to count the number of basically pulses coming from the sensor. PLC counter instructions are similar to timers, except that they do not operate on an internal clock but are dependent on external or program sources for counting. Here we have an up counter, and here in this contact is, let's say, is a push button. Every time that this contact becomes true, this counter counts up. Okay, and the accumulated counter value will increment by 1. And this is a preset counter value. So when the accumulated value reaches to the preset value, then the down bit of the counter becomes true. Generic coil formatted up counter instruction is shown here. The counter reset instruction must be used in conjunction with the counter instruction. So here we have a counter, and here we have a counter reset that uses the same address. Okay, and this is a push button or the contact to reset the counter. So if this contact goes through from false, the accumulated value will back to 0. The counter reset coil is given the same address as the counter that it is to reset. Up counters are always reset to 0. Generic block formatted counter. All PLC counters operate or count on the leading edge or off to on transition of the input condition. Okay, so here we have our input module. We have one sensor as a proximity sensor and one push button for reset. And we are going, let's say, to count number of items passing by this proximity sensor. So every time that the sensor goes true, from false to true, then the counter will count up. Okay, and it will increase the accumulated value, will increment up until it reaches to the preset value. And we could reset the counter at any point by pushing the reset button or this push button. PLC counters can be programmed to count up to a preset value or to count down to a preset value. So up counter and down counter. Okay, the up counter is incremented by 1 each time the rung containing the counter is energized. So every time this switch, this limit switch here is energized and we have a pulse, then the accumulated value will increment by 1. The down counter decrements by 1 each time the rung containing the counter is energized. Okay, so it should always be energized for both cases from false to on. But the difference is that down counter will decrement every time. Okay, the decrements. So here we have, let's say, -5 here. And again, by resetting, the counter will back to 0. So for both of these cases, when the accumulated value reaches to the preset value, then the output of the timer becomes true, or the down bit of the timer becomes true. Up counter. The up counter is used to count false to true transitions of an input instruction and then trigger an event after a required number of counts or transitions. Okay. The up counter output instruction will increment its accumulated value by 1 each time the counted event occurs. Okay, so when the accumulated value reaches to the preset value, then the down bit of the timer becomes true. SLC 500 up counter program. So here in our inputs, we have count button and we have a reset button. And we call the count 1 PB1, push button 1, and reset push button 2. And as you could see here, push button 1 will increment the accumulated value. Preset value is 7. Okay, so here you see we are using the same address for this counter. This one is the counter number 5. And this is a down bit. So when it reaches to the 7, the accumulated value reaches to the 7, the red pilot light goes on. Okay, while it's basically incrementing from 0 to 7, before it reaches to the number 7, the down bit is false and negated contact of the down bit will be true. So the green pilot will be on. And when we press the push button, the counter will be resetted to 0. And you could see we are using the same address for the down bit and for the reset coil. So let's see what happens here. This is a wrong one, and we are pressing and releasing the push button, the count push button or push button 1. Before it reaches to number 7, see that the wrong 2 is false, but wrong 3 is true. And then when it reaches to the 7, then the 2 goes on and 3 goes false. Wrong 4, push button 2 is not pressed from the beginning to here. Okay, so and here is press, and once it's pressed, you see that the wrong 2 goes false, or the red pilot light goes false and the green pilot light goes on. Why? Because the down bit basically goes false or becomes false. And here you could see how the accumulated value is incremented up, and when it reaches to the number 7, here at this point, what happens to rung 2 and rung 3, and once the reset push button is pressed, it drops to 0. The Allen Bradley SLC 500 counter file is file 5. This is specifically for the Allen Bradley and not for Siemens, for example, PLCs. So in TIA portal, you don't have specific file for counters as we have in Allen Bradley. Or in codices also, we don't have this type of filing, yes? So this is specifically for these type of PLCs. So here, for example, see we have a couple of counters in file 5 from 0 to 5, and we could watch or observe the status of, let's say, count up, count down, and accumulated value, and preset value, and etc. So the preset value in this case, for example, is 50. So here we have a count up enable bit is true whenever the count up counter instruction is true. So whenever we push the count push button, this one becomes true. Count down enable bit is true whenever the countdown counter instruction is true. And down bit is true whenever the accumulated value is equal to or greater than the preset value of the counter, or either the count up or the count down, so it doesn't matter. Yeah. So some counters are a combination of up and down counter, and both of these bits could be energized, and at the same time it could increment at decrements. Overflow bit is true whenever the counter counts past its maximum value, 32,767. This one is basically 2 to the power of 15. Okay, and because as a 16 bits, on the next count, the counter will wrap around to minus 32,768 and will continue to count to 0. So we should be careful of this overflow bit, otherwise the program might not work. Underflow bit is true when the counter counts below minus 32,768. The counter will wrap around to 2 to the power of 15 and continue counting down towards 0. Okay, and this is the maximum value specifically for this Allen Bradley PLCs. Other PLCs might have a bigger or smaller maximum value. Updated accumulator bit UA is used in conjunction with an external high-speed counter. So these UA is used for counting high-speed encoders, for example. Okay, and the preset value PRE specifies the value that the counter must count to before it changes the state of the down bit. So we had a couple of examples before, so you should know the concept of this one perfectly. The accumulated value ACC word is the current count based on the number of times the run goes from false to true. So it's basically the last updated value of the counter. And when the ACC reaches to the preset value, then the down bit of the counter becomes true. SLC 500 up counter instruction, you could see the block diagram of the up counter, and you could see the down bit here. For this case, preset value is 10. This is basically the counter up enable bit. Okay, so whenever or when this contact goes from false to true, then the counter increment by 1. The down bit, when the accumulated value reaches the preset value, down bit becomes true. The overflow status bit, this is basically when the accumulated value reaches to 2 to the power of 15, and the reset instruction resets the counter accumulated value back to 0. Okay, so we need always to reset counters, either up counters or down counters. Up counter instruction in codices, you could see for count up, for the reset, okay, and for the down bit, okay, and the CV is a current counter value. And you see that how you could drag and drop it to your rank, okay, where you could find it in function blocks, either counter up or counter down. PLC counter program used to stop a motor from running after 10 operations. So here we have our inputs. Inputs start and reset. And here we have our output motor. So if we start the motor once and stop it, the counter will increment by 1. And if we continue this starting and stopping, then the counter will continue incrementing up to reach into the preset value. Okay, so once we are at the preset value 10, the down bit becomes true, and the negated value of the down bit here will be false. So the logic here will be false, and the motor will shut off permanently. So there is no way to start it again by the start button until we reset it or reset the counter. Okay, so if you reset the counter, then the start button will work again normally, and the stop button as well. Can counting program that uses 3 up counters. Here we have a conveyor and cans moving on the conveyor, and there is a proximity sensor that senses these cans and sending pulse signals to the counter. Here we have our inputs. We have proximity sensor and a reset push button. So proximity sensor sends pulses to the counters. So the first counter is for counting parts. On each box we have 10 parts, and the second counter here counts the overall number of parts. So once the first counter is done, the down bit becomes true of the first counter. Look for the address of the counter. We have C51 here, and we are using the same C51 here. So once the down bit becomes true, then the coil here, or the motor that should close the box, will close the box. So we have 10 can in one box. And when we close this box, okay, so we count, this counter will count the number of boxes. So the number of boxes, okay, here multiply by 10 plus the value of the accumulated value of the first counter should be equal to the accumulated value of the C52 counter. Okay, so once we press the reset button, then C52 and C53 both will be resetted to 0. Plus, once the down bit is true, then the counter itself will reset itself. Yes, so the down bit of the counter will reset the counter. Okay, so we don't need to reset this counter automatically. It will be resetted once it reaches to the preset value. A one-shot or transitional contact is often used to automatically clear or reset a counter. The one-shot can be triggered from a momentary signal or from a signal that comes on and stays on for some time. So here we have our input A. Okay, so this input A will create a pulse in one-shot output. How that happens, we have an internal relay coil. Okay, so this is the internal memory, and since we have a scanning, and the scanning goes from top rungs to down rungs. Yes, so the first rung is here while we are scanning. So when the input A becomes true, the internal coil is not yet true because we are in the up rung. Yes, so the negated value of that internal relay coil will be true, and the one-shot output becomes true or becomes on. Yes, but few moment after, few millisecond, less than millisecond, it depends on the speed of scanning. Since the A is true, the internal relay coil becomes true, and then in the next scan, now the negated value will be false and the one-shot output becomes false. Okay, so this one-shot output stays basically on or true only for one scan time. So it stays on for one scan only and then goes off. It stays off until the trigger goes off and then comes on again. So we use this type of coils to reset or counter. Some PLCs provide transitional contact or one-shot instructions. The off to on transitional contact provides a one-shot pulse when the trigger signal makes an off to on transition. Okay, so in some PLCs, we don't have to program those type of transitional contacts is already provided in the programming environment. You could see the symbol, and once we trigger it, okay, so once basically the logic behind that transitional contact comes true, then that transitional contact stays on for only one scan. You have also opposite of off to on, and there is on to off transitional contacts, and they provide a one-shot pulse when the trigger signal makes an on to off transition. Okay, so the trigger signal here goes from on to off, but the transitional contact stays on for only one cycle. Yes, so for both of these cases, it stays on for one cycle. The difference is the way they should be triggered. The first one, the signal should go from off to on, and on the second one, it should go from on to off. The Allen-Bradley SLC 500 one-shot rising instruction is an input instruction that triggers an event to occur one time. So here, this is again a one-shot rising, or the transitional coils. Here we have a limit switch input, and here we have our one-shot rising contact. Again, when the LS1, or that limit switch, goes from false to true, or send a pulse, yes, then this B3, which is our on-shot rising contact, goes from false to on for only one scan time. And that is enough to reset or counter, and in the next scan, again, this one will be false, and it doesn't matter what is the value of the limit switch. It's true or false. Up counter with the program one-shot rising off to on transitional contact instruction. Okay, so here in this program, we have stop, start, and proximity sensor and reset push button. The proximity sensor here, as you could see in the picture, sends a pulse whenever we have boxes. Yes, so when these boxes passes from the proximity sensor, and then the proximity sensor sends a pulse. But the I13 is the address of the proximity sensor. So when it goes from off to on, then the off to on transitional contact becomes basically true for only one cycle. Okay, so for only one cycle, and the reason is that it's for the safety, for having more reliability of the program, and the counter will increment one. Okay, these are basically the ways to reset the counter. Okay, and this drawing, and here in this drawing, the O20 is the motor, and what is the motor? Is the conveyor motor. Okay, so when it reaches, for example, when the counter reaches to the 50, then the conveyor stops. The OSR instruction used to freeze rapidly display LED values. Here we have a timer. Okay, so that switch here triggers the timer, and the accumulated value increases rapidly, goes up. Here we have the LED output. You see what is the source? The source is accumulated value of the timer. So this LED basically displays the accumulated value of the timer. And see that this destination is 06 or the output 6 here. Okay, so this TOD is this display. Okay, so we want to stop the display for a moment to see what is the value on the display because it goes up very quick. So we want to freeze it for one scan time. What we could do, we could use this OSR. So when we press the push button, the OSR goes false here and stops the display for one scan time. Okay, and then again for the next scan, it will continue showing normally the time. Alarm monitor program. Here we have a level of water, and this sensor that measures the level of water. This is our sensor. This is the symbol basically of that sensor, and we have this switch here that could switch from on to off. Okay, here the first two rounds we are using two timer and using the downbeat of the other ones to trigger them. Yes, so we had one example before. This is basically annunciator, and we're going to use the annunciator to flash this light. It goes from on to off, and here you see how we are using the downbeat of them to flash this light. So here we have the downbeat of the counter, and the counter preset value is 1. So if this lever sensor triggers once, then the downbeat of the counter also becomes true and the lights start flashing. And finally, if we want to reset this alarm monitor program or we want to stop the light, we could just turn the switch from off to on and reset the counter. Down counter. A down counter will count down or decrement by 1 each time the counted event occurs. So it works almost the same as up counter, but it's opposite. Yes, so instead of incrementing the value of the accumulated value, we could decrement the value. And here we have up down counter, combination of both up counters and down counters. The push button one is press, the accumulated value increase by 1, and if push button 2 press, the accumulated value decreases. Normally, the down counter is used in conjunction with the up counter to form an up-down counter. Up-down counter program counting diagram. Here we see how the up-down counter works. The preset value is 3. Here we have all pulses that triggers the up counter. So 1, 2, 3. We already reached the preset value, and the output goes from off to on or false to true. Okay, then we start and then we continue. Okay, so this up counter continues to 5, 4, 5, 6, but it doesn't change the output of the counter because it's already over the preset value of 3. Then we start to trigger the down count bit, and 1 pulse, second pulse, third pulse, and at the fourth pulse, the preset value drops below 3. So at this point, the output goes false. Okay. until we press the reset button. And once we press that reset button, then basically the accumulated value will drop to 0. Okay, so this is the accumulated value that already dropped to 0. Parking garage counter program. Here we have our inputs. We have enter switch, proximity sensor, exit switch, proximity sensor, and reset. So this one is installed at the entrance, and this one is installed at the exit of the garage. And this one is used for resetting the counter. We have up counter that is triggered by the enter switch, and down counter is triggered by exit switch. And once the up counter here reaches to the preset value of 150, which is the capacity of the garage, then the lot full light here goes on. Okay, so this one goes on and stays on until we reset the counter. Countdown counter instruction used as part of the SSC 500 counter instruction set. Here we have a block diagram of the countdown counter. The counter enable bit, okay, so shows if the counter is triggered. The counter down bit once the accumulated value reaches the preset value, and we have an underflow start speed. So if it reaches to the maximum value of the counter that goes on, and the reset instruction. The information to be entered into the instruction is the same as for the count up instruction. Okay, so these informations are same as up counters that we already explained. Down counter instruction in Codice is very similar to the up counter. Drag and drop from function blocks to the wrong, and you have a countdown, down bit, accumulated value, preset value, and the load here. Okay, and the load is basically load start value. This is the value that we start to count down from. For example, okay, so by default is 0, yes, so we start counting down from 0, but the load value could be something other than 0, for example 10, and when we count down it starts to decrement from 10 to 9 to 8 and so on and so forth. Up down counter program. Here we have up counter and down counter with the preset value of 10, and we have push buttons to trigger each of them. And we have 3 LEDs, A, B, C. We could monitor the performance of these counters one by one and see how we could also reset the counters. Up down counter instruction in Codices. So here in function blocks, we used to get the count up and count down function blocks, but instead of using those, we use a box, okay, with the enable in and enable out. Okay, so we use this one. So here we have our box. We need to click on these question marks and set what is the type of that box. Once we click on that, then we could choose the type of the counter, which is count up down counter here, and press OK. So here we have our counter now, and what we need to do, we need to just choose a name. Okay, So we need to choose a name, and then the counter will be displayed on the auto variable declaration form. Okay, so that will be displayed there. Here we have our counter now, and we could set any of these values, load and preset. Here we have the detail instruction of each inputs and outputs, very similar to up counters and down counters. Program that provides continuous monitoring of items in progress. Here we are using two sensors, one for the input materials or infit parts, and one for outfit parts or output materials. The accumulated count of the counter continuously indicates the number of in-process parts. So here inside this box or machine, the process parts, we don't know what is the process, yes. For the purpose of this example, doesn't matter to us. What we want to monitor here is basically how many of these parts we have in process. So to slow or to speed up the conveyor and see how many of the how many parts we could feed into the machine. Part that provides continuous monitoring of items in progress. So for the previous slide here, see how we could use up counter and down counter. So this is the infit count and this is the output count. Okay, so accumulated is equal to the number of in-process parts. Okay, so this is a basically up-down counter in combine. So once the infit count triggers, yes, so it increment up by 1 and then decrement by one. Cascading counters. Depending on the application, it may be necessary to count events that exceed the maximum number allowable per counter instruction. One way of accomplishing this count is by interconnecting or cascading two counters. Okay, so let's see how it works here. Counting beyond the maximum count program. So in many PLCs, we have a limitation on the preset value. Usually this number is 2 to the power of 15, okay, so almost 32,000. So here we are using two counters, and this counter goes up until it reaches to 32,000. Once it reaches to that value, okay, so this is this one, okay, so this counter reaches to that value, the down bit becomes true. Once the down bit becomes true, then this counter goes up by 1, okay, and this counter will be resetted to 0 again. Okay, so by this way, we could go beyond this 32,000 because we know how many of the overflow we had in past, and the number of parts is equal to the value of this counter multiplied by 32,000 plus the value of the second counter. Cascading counters for extremely large counts. You could see again we are using two counters, and the same methodology is used here also to go beyond the maximum values and see how we could reset these counters. So very similar to the previous scheme, this one as well. 24-hour clock program. Here we have combination of timers and counters. The first block here shows the number of seconds pass, and the second one, the counter shows the number of minutes. So when it reaches to 60, it triggers this one by one only, and the second one hours. When the value of the minutes basically reaches to the preset value of 60, then the hours counter will increment by one. Okay, and see how we are resetting them. Okay, so for example, for the first one, when the down bit is true, it will reset itself automatically because it needs to back to 0. For the C50, this one, again, once it reaches to the preset value of 60, then it resets itself. Okay, so, and for the last one, for the hours, also when it reaches to the 24 hours, then it resets itself to the 0. Okay. Incremental encoder counter applications. The incremental optical encoder creates a series of square waves as its shaft is rotated. Okay, so here we have a shaft. This is a shaft of a motor, or the rotor is connected to the rotor of the motor. And here we have our optical encoder. You see there is a disc, and the disc is attached to the rotor, and there is a light source. Okay, so this light source here will be interrupted by the disc. On the other side of the disc, there is an optical sensor. Yes, and this disc causes interruption and then creates these generated pulses. So these pulses should be counted by the PLC or the counter. Encoder disc interrupts the light as the encoder shaft is rotated to produce the square wave output waveform. So here we have one example of using encoders cutting objects to specified lengths. Here we have the conveyor and the woods seat on the conveyor, and the motor or the drive motor of the conveyor has an encoder, a rotary encoder, the optical encoder. Okay, and the optical encoder sends these pulses to the PLC. By having or counting the number of pulses, we could know how far we push these woods forward under the cutter. The object is advanced for a specified distance and measured by a counter pulse to determine the correct length for cutting. Counter program used for length measurement. Here we have our conveyor, and there is a sprocket here to drive the conveyor forward. And there is a magnetic sensor here that is triggered by the tips of the teeth. Basically, teeth of the sprocket. The teeth of the sprocket triggers the sensor. Okay, so we could count how many of these teeth already pass from the tip of the magnetic sensor. Okay, so let's say the speed of the motor is constant. By counting the number of pulses coming from the sensor, we could measure the lengths of the parts. This is what we are doing here in the program. We have magnetic sensor input, and the photo sensor basically it sends if there is any part or not. Okay, and once there is a part, okay, once there is a part, then this up counter starts to count the number of pulses coming from this magnetic sensor. Combining counter and timer functions. Automatic stacking program. Here we have two conveyor, and the goal is to pile these plates, and the number of plates on one stack should be equal to 15. Okay, so we have one sensor here, and we have conveyor 1 and conveyor 2. So conveyor 2 should stop while the conveyor 1 is stacking. Once the stacking is finished, the M1 should stop and the M2 should move forward. So here we have one up counter here that counts the number of plates coming. And this sensor basically measures if or checks if the plate is arrived. Okay, and once it's done, then the motor 2 will start. Okay, so the motor 2 will start because we need to push this stack forward and stack or start to stacking plates again. Okay. So here the downbeat is used, okay, to start the M2, and the M2 is on, so the timer starts to time for 5 seconds. Once the timer is done, okay, then the counter will be reset to 0, and the M2 motor will stop. Okay, so the M2 motor also will be stopped and the M1 start again. Product flow rate program, counting the number of items in 1 minute. So here we have a counter, and here we have our timer. The preset value is 60 seconds. So we want to know how many of these parts passes in front of the sensor. Here, this is our sensor in only 1 minute. Okay, so when we press the start, the timer also starts, and okay, so here we have a sensor input, so the counter starts to increment up. Once it's done, the downbeat becomes true, and then this contact, the negated one, becomes false, and the counter will stop. So now we know how many parts pass in 60 seconds, and that shows the rate or the speed or the flow rate, basically. Timer driving a counter to produce an extremely long time delay period. So here we have our timer and counter. Okay, so the preset value here is 10,000 seconds. Once it reaches to the 10,000 seconds, it will trigger the counter by 1. Okay, and then it will be reset to 0 again, and again counting up. Yes, so if you multiply the number of accumulated value in the counter by 10,000 and add it to the accumulated value in the timer, then we know how many seconds already passed. So by this way, we could exceed the maximum value of the preset value in the timers and have extremely long time delay period.